This is part 2 of section 6.4, gradients and directional derivatives. In part 1, we learned what a gradient is. In this section, we're going to learn, or in this video, we're going to learn what a directional derivative is, and then we'll calculate an example, and we'll do a couple more examples in the next video. And so, we start with this definition, and at first it looks a little unwieldy. So we have a function f from Rn into R. We have a point in Rn, and we have a vector in V sub n. And so what we have defined here is the directed derivative of f at c directed by v. Okay, that's kind of a mouthful, right? But it's written out in your notes. And so what we do is we take the limit as h goes to 0. We don't have a vector, so we're not looking at magnitude of h going to 0. H is a real variable. So we have the limit as h goes to 0. F is a function of n variables. So we have c sub 1 plus h times v sub 1, where c sub 1 is the first coordinate of c, and v sub 1 is the first component of v. And then we have c sub 2 plus h times v sub 2, and again, c sub 2 is the first it's the second coordinate of c, and v sub 2 is the second component of v. We do this for all n, so we get down to the nth one, then we subtract f of c. Now remember, f goes from Rn into R, so this thing is a real number. This is a real number. We divide by a real number. We're taking a limit in R. So we just have a number minus a number divided by h. So we have a limit in R. So essentially this is going to boil down to a calculus 1 or a calculus 2 problem. And that is what our directed derivative is. Now, in the case that v is a unit vector, then we call it a directional derivative. And in most cases, we want v to be a unit vector. And so if we're asked for a directed derivative, then we're not picky about the magnitude of v. But if we're asked for a directional derivative, v has to be a unit vector. So if you're asked to find a directional derivative and your vector is not a unit vector, you have to divide by its magnitude to make a unit vector in the direction of v. Now, even though this looks a little bit difficult, if not messy, as usual, when we have a derivative, we have a nice theorem that comes afterwards, which tells us that calculating this limit's not as bad as it seems. And that's what theorem 181 is. Our directed derivative of f at c in the direction of v, if it exists, and we always have to say if it exists when we define something in terms of a limit, is really the dot product of the gradient of f at c and v. That's all we do. So for example, 182, part A, g of x is this polynomial right here. We want to find the directional derivative of g at the point -1, 2 in the direction of u, which is the vector 1/2 square root of 3 divided by 2. Notice this is a unit vector. 1/4 plus 3/4 is 1, and so the magnitude of u is equal to 1. Calculate the partial derivative of g with respect to x. Calculate the partial derivative of g with respect to y. Use these partial derivatives to calculate the gradient of g at the point -1, 2. And so the gradient is the vector -2, 1. And now the derivative is simply the gradient of g at the point 1, 2, the dot product of this vector with u. Remember, dot product's a number. So this derivative, this directed derivative, or in this case it is a directional derivative of g at the point -1, 2 in the direction of u is a number. So we simply calculate the dot product of those two vectors. So we have -1 plus square root of 3 over 2. And then I wrote it a little bit prettier there on the end.